Okay, so today I want to talk about the topic of trig identities and more specifically how to approach these kinds of questions. But in order to do so, I kind of want to go back to one of the most basic trig identities, commonly known as sine squared x plus cosine squared x is equal to 1. And commonly in the classroom, this formula is mostly just given out as something that we should just know. But I think it's better to actually visualize it and more analytically see how this formula comes together. So on the left, you can see that it's a picture of the unit circle and with a right triangle with angle theta. So we can see that this side is equal to sine theta and this side is equal to cosine theta because sine theta is equal to this side, the opposite side over the hypotenuse, and then cosine theta is obviously adjacent over the hypotenuse. And the hypotenuse is equal to 1 since this is a unit circle with radius 1. So by Pythagorean theorem, we see that sine theta squared plus cosine theta squared is equal to 1. And we can see this more algebraically in order to prove this is actually true. So you having a right triangle here with sides A, B, and hypotenuse C, we see that a squared plus b squared equals c squared by Pythagorean theorem, and sine theta is equal to a over c and cosine theta is equal to b over c. Now we can plug it into this equation that we found here. So sine theta squared plus cosine theta squared equal to 1. So a over c squared plus b over c squared is equal to 1. So a squared over c squared plus b squared over c squared is equal to 1, and a plus b over c squared is equal to 1 by like terms. And then now we see that the top, by the top we have the a squared plus b squared is equal to c squared. So c squared over c squared is equal to 1. And we can see that this is true because c squared is equal to c squared. So this is true. And now we'll see how to actually approach a trig identity problem here. So let's say we have the problem cosine t over 1 minus sine t is equal to 1 plus sine t over cosine t. And usually how we want to approach these kinds of problems is to take one side. The side is more seemingly complicated, has more terms, etc. And you want to somehow find a way to algebraically and using other well-known basic identities to get a more complicated result. So as you can see, with this problem, I'm going to choose the left-hand side. I'm going to choose the left-hand side because to me, I feel like I can work with it more. And before you want to attack this problem, you want to see, oh, what identity do I already know? And do I see something similar in this problem? So if we take the left-hand side specifically, we can actually use the identity that we've proven up here. Because the bottom has 1 over sine t. But this isn't exactly what we want. We want 1 minus sine squared t because we get that, we can get the bottom here, cosine t. So how is it possible that we can get from 1 minus sine t to 1 minus sine squared t? So 1 minus sine squared t is actually a difference of squares, 1 minus sine t times 1 plus sine t, which is something just like a more basic algebraic thing rather than a trig identity. But it's the same concept because we can treat this almost like our typical variables that we've used before. So in order to get cosine t over 1 minus sine squared t, we have to multiply it by 1 plus sine t on the bottom. So we're going to do that, but we have to keep the top and the bottom the same, so we multiply by 1, which is equal to 1, obviously. And then you want to multiply these together, so multiply the top, and then we'll get our 1 minus sine squared t on the bottom, which is on the bottom is equal to cosine t, which we want to find. So cosine squared t, sorry. Oops. So now we see this, right? And we're now realizing we can get to cosine t on the bottom based off of having cosine squared t, because the top also contains a cosine t. And as you can see, the top and the bottom are now both the same as what we wanted to solve. So cosine t over 1 minus sine t. And it's okay to be like afraid of approaching these kinds of problems at the beginning, since it may seem complicated, but if we just take a step back and use what we already know, then it's actually not that intimidating to solve.